Hi, good morning, good afternoon, good evening, depending on where you are in the world. Welcome to Micromaterials' latest seminar on nanomechanical measurements. Today we're looking in particular at nanomechanical characterization at high temperatures and how to understand your materials at elevated temperatures. If you're interested in micromaterials, you can find more about us on our LinkedIn pages. That always contains details of our seminars, latest publications, technical publications, and other such things that we release, such as application notes and collaborative notes. I think that's a good place. Otherwise, the web page is also there at micromaterials.co.uk. You might know that we were formed in 1990 and have specialized in nanomechanical measurements for the last 31 years, I guess that makes it, and have basically very versatile instrument at the leading edge of science, and very modular and compatible with what high-end research needs. And one of the particular areas that we are interested in and do have expertise in is the high temperature air measurements, both in ambient and vacuum situations. Speaker today is Professor Ben Beake, who has worked with micromaterials since 21 years, I think, if memory serves me right, maybe 22, to that time has taken on as applications director, and has worked in collaboration with many universities around the world, developing applications and techniques and hardware as well, which is now in use in many other places. So with that, without much ado then, I will hand over to Ben, and Ben will take you through the presentation. At the end, we will have questions. The easiest way is to write your question in the chat box, which Sam has started off, and also it's good to know where you are, where you're calling from, so do put hello in there, any questions will go in there. They will be picked up and they will be queued and they will be dealt with at the end of the seminar. So therefore I'll hand over to Ben and for the talk.
Thank you very much, Chris. And okay, so welcome everybody. So if you're in the east coast of the US, thank you very much for doing this in your lunch hour. And I guess if you're on the west coast, thank you very much for doing this when you otherwise might be having breakfast. So very appreciate that. So I'm going to be talking about solving the challenges in high temperature nanomechanics, and particularly at higher temperatures, because the challenges get more extreme as the temperatures go up. So I'll start off by introducing why we might be interested in studying high temperature nanomechanical testing. This is partly applications driven and partly fundamental interest in the temperature dependence of mechanical properties. Then I'll be summarizing the main challenges that you need to meet to achieve reliable high temperature nanomechanical testing. So those are around thermal stability, around environmental control, and around improved data analysis to combat the increased time dependent deformation. And then I'll give application examples about where we can meet those challenges, particularly at higher temperatures, and give some examples where we've used the NanoTest system and our customers have used the NanoTest system to test up to 750 degrees Celsius in inert gas environments and up to 1,000 degrees in a vacuum environment. And then I'm going to finish off by discussing some future research directions in the technology. So that's going to be both looking about where we might be going in terms of temperatures and also where we might be going in terms of other different nanomechanical tests that we now are achieving now, have that capability at high temperature. So when we think, so one key application area is in understanding the mechanical properties of hard wear-resistant coatings. And a lot of these applications, hard PVD and CVD coatings need to combine high hardness with high toughness. So you might see a schematic such as this one here that I've taken from this paper by Sam Zhang towards hard yet tough ceramic coatings, where the idea is that to some extent that you might be able to produce coatings that are not quite as hard as possible, but they nevertheless combine a certain amount of toughness. But that picture is to some extent somewhat incomplete when you consider that in many of these applications, it's really not the room temperature hardness that's the critical thing, but it's the sort of high temperature hardness and toughness combination that really delivers that high temperature wear resistance in the application. So that's the critical thing for many of these applications. So as we have now the capability to do these measurements now, we should therefore improve our optimization and to develop better materials. So one particular application where high temperatures are involved is in high performance machining applications. So in these applications, the frictional heating generates a lot of heat. So this slide shows, first up on the left, that's a thermal image of a cutting tool insert during cutting a carbon steel in a continuous turning application. And what you can see there is that really very high cutting temperatures are generated near the surface of this aluminium-rich titanium aluminium nitride coating that's deposited on the cemented carbide surface. And those high temperatures are typically on the flank face, or the highest temperatures on the flank face. So there in this application, you're really going well up to sort of about 900 degrees. But potentially in other applications that are still very tribologically extreme, such as end milling, in this case of a titanium 6-4, which is considered a hard to cut material. In this case, it's a very, very similar coating. In this case, it's not an experimental result. In this case, it's a finite element model simulation of the cutting temperatures. And here from a group in Greece. And here you can see at this slightly lower speed, but nevertheless still very fast, 100 meters per minute, you can see that you're still achieving several hundred degrees cutting, and that interrupted cutting allows for a certain dissipation of the temperature before you recontact. So you have quite a wide range of cutting temperatures, and it's important to understand what the temperature is in your application, and therefore to optimize your coating for that. So if we take three different coatings that are used in these applications, typically as shown here, what we can see is if we rely just on the room temperature data, then they fall in a reasonable band of sort of 25 to 30 gigapascals hardness, which is perfectly adequate. But if the frictional heating in the application raises the temperature up to say 500 degrees, what we can see here is that the red coating there is much less thermally stable than the other two, so therefore its performance is very likely to be, and indeed is much worse in high-speed metal cutting than these other newer developed coatings that you see there that have a better high-temperature performance. So it's worth pointing out that when I plot on the x-axis here temperature, really what we're describing here is the test temperature. So we're actually measuring the mechanical properties of the coating at that temperature. We're not subjecting the coating to an aging process at temperature, which may age harden it, anneal it, change the microstructure, and change its mechanical properties when cooled back down to room temperature. But when you're actually testing at temperature, then you have some thermally activated dislocation motion in there, and typically materials can soften quite dramatically. So when you do these measurements with a nano-indentation system, it gives you lots of opportunities to really study materials properties in detail. You can have the ability to get precision sensitive local mechanical mechanical property data as a function of temperature. If you look in the middle of the slide at the top, you can see an indent placed in a cemented carbide grain right in the center there, and you can see a focused ion beam mill of that to confirm the grain structure underneath that indent. You can also look at pileup changing as a function of temperature. You can look at toughness flame changing as a function of temperature. You can study brittle ductile transitions, changing plastic deformation mechanisms, and rate sensitivity. And there's a wealth of different things you can look at. So coming back to basic high temperature nanoindentation now. So there are several key factors that you need to understand to deliver reliable high temperature data. The first thing really is instrumental stability. So the critical thing is essentially that you have a design of instrument which is stable, so the heating stage is essentially remote from either the loading or the displacement measuring electronics. And another critical thing that we realized quite a long time ago at Micron is that it's really, really useful to have a so-called isothermal contact. So in other words, that we have minimal or no heat flow when we actually do an indentation test. And if we can achieve that, if we can have a situation where the indenter and the sample are at a thermal equilibrium, then we can achieve a thermal drift measurement that is essentially the same as it is at room temperature. The other things that we need to consider are what happens to the stability of the indenter material. In this case, is related to oxidation temperature. Also, tip sample reactivity is also important. We need to consider the bonding of the indenter and make sure the indenter remains well bonded into its holder at high temperature, and also the wear resistance of the indenter. We need to consider the environment, test environment. Does the sample oxidize? Do we want to run in an inert atmosphere? Do we want to run in a vacuum environment? And lastly, we need to understand that we potentially get, even if we accurately control and account for thermal drift, then the deformation mechanism that we get may be more dominated by time-dependent deformation than analogous results at room temperatures. And that even can be for systems where, like hard coatings, for example, where you typically wouldn't assume there is any time-dependent deformation, and where you can design your experimental loading history and also your analysis to mitigate these time-dependent deformation approaches. So if you, so this is kind of what not to do. So if we just have a simple thermal model where we simulate a hard diamond indenter in contact with a conductive, metallic conductive sample, in this case gold at 300 degrees Celsius for 8 hours, and we only heat the sample and we rely on passive heating of the indenter probe, then it would be, if it was possible to achieve a nice thermal equilibrium without actively heating the indenter, then we could reliably do measurements by just heating the indenter. What this sort of slide shows you is that when you only have this so-called passive indenter heating, that you typically get very high temperature gradients through the sample, and these get increasingly worse as the temperature goes up. So the solution to this is to avoid these temperature gradients by so-called dual active heating, where we separately heat the indenter and the sample. So this slide shows a schematic where we look at the hot stage configuration in the NanoTest system. So for those that don't know, it's a horizontal loading configuration, which gives some advantages when it comes to doing these things, because any heat that's rising through convection is moving away from the displacement, displacement electronics. So if you're indenting from the top, then potentially your heat flow from convection would be coming up into your displacement measuring sensors. So that's not an ideal situation. And so here it shows that we have it's shown schematically with separate active heating of the probe and the sample. And we can have thermocouples on the indenter and the sample to record those temperatures. And what isn't shown here, but what we can also do, and often we do, is to have a separate thermocouple actually on the sample surface. So that sample thermocouple is not for control, it's just for providing an accurate measurement of the surface temperature. So by doing this, we can with this sort of hot stage device and with this shroud, we can achieve what we call a localized hot zone for an isothermal contact. So the shaded area that you see there, essentially throughout that shaded region, essentially we have relatively very close constant temperature. So it's designed really not to dissipate the heat, but really to keep the heat into that zone to minimize any thermal gradients within it. So we have a patented way of controlling the tip temperatures. Essentially, we do that instead of it being PID control on both tip and sample. In the final, before we do the testing, to allow for the different thermal masses of the indenter on the sample, we have a power lock method where we lock the power within a tight band on the indenter when we actually do the indentation. And this avoids essentially having two PID loops that fight against each other. And that delivers much better data quality. The stage itself is patented as well. And you can see there you have these thermally isolating silica supports. And what they do is that they they allow the back of the indent, that stage, to be really at room temperature, sort of 2 or 3 degrees higher than room temperature. If you put some thermocouples on when you're up at say 750, 800 degrees, you can confirm that really you're basically at room temperature at the back of that stage. And that's very useful, because that then allows you to put a nanopositioning stage on the back of that. So you've got 2 stages together, and that nanopositioning stage, as I'll show you later in the talk, gives you a lot of flexibility in terms of very accurate positioning and targeting of key features at temperature. So if we look now at the sort of load history that we might want to do, so we borrow a sort of ISO 14577 type approach to thermal drift correction. Essentially here, we're allowing for the fact that creep is more significant at high temperatures typically. So we can improve the accuracy of the thermal drift correction by a couple of things, by increasing the hold time to eliminate any influence of creep recovery, which typically occurs, as shown there, in the sort of first 20 or 30% of a whole percent at 90% unloading. And we can also it's also beneficial to increase that hold time when we're running longer tests, typically, to improve that accuracy. So this is an example from some work that my colleague Adrian did in collaboration with the University of Oxford. And what you can, this is a vacuum system, so they were looking at polycrystalline tungsten samples at up to about 950 degrees. And you can see there's the heated indenter, and you can see how it's glowing hot at these very high temperatures. And so that what we're looking here at essentially is just the hold period data. So if I go back, so we're looking at the depth, what happens in the depth while we're holding at 90% unload. So this is just analogous to what we do in ISO 14577 at room temperature. And this is just trying to understand and convince ourselves that we have minimal thermal drift. So what you can see typically in a hold period like that is that when you have a lot of creep recovery, which you might see on a polymer at room temperature, for example, viscoelastic recovery, then you'll get a lot stronger initial decrease in depth when at higher load, because it's a material response. So the idea essentially is that here, that this creep recovery process essentially creeps out after the first 20 seconds or so, and then you can lose the last 40 seconds of the data for an accurate thermal drift correction. So this is an example here where this is a small subset of many measurements done where we were able to show that this thermal drift, we had basically thermal drift around 0.05 nanometers per second, really right up to 950 degrees C across the entire temperature range that was done. So it's basically very thermally stable, and then we can start to look at materials effects. So moving on now to looking at the indenter. So diamond is a very popular choice because obviously at room temperature it's very hard, it's very, very durable, it wears very minimally. And this is an example in this case from a paper from Wheeler and Mickler. And this is an example AFM image of an indenter. I think this one was from the University of Cambridge. And this has been used for an awful lot of testing, but at temperatures under 400 degrees. And what we can see here is that the Berkovich geometry is retained. So it's basically not wearing. But when we increase the temperature, then there's oxidative degradation of that diamond material. So this is an example of some pitting that you see at the surface. This is after just 90 minutes in 900 degree in argon at 900 degrees. So this has not been in contact with the sample. This is simply diamond degradation through the residual oxygen that is in there in this in the argon environment. So another thing that can cause a problem is you think about tip sample reactivity, and you don't essentially want to be indenting carbide formers with diamond at high temperature. So this is an example of, if you can just see there on the right, that the very edge of that tip has been completely sort of destroyed eroded away by the interaction with the sample essentially. So this indenter was basically destroyed. So we want to basically avoid using diamond at too high temperatures, and we want to avoid using diamond on materials that it's going to react with. We can use diamond when we have relatively little choice. In this case, this is on it's a tristructural iso nuclear fuel, and essentially the silicon carbide in this multi-layer pellet essentially it's very important to understand how its mechanical properties change with ion irradiation in, for example, a high flux reactor. So some work done here from the University of Manchester here in the UK, and they were comparing what's described here as pristine silicon carbide with the irradiated silicon carbide. And what we can see here is typically on this hard material, its decrease in hardness is relatively small over that temperature range, but nevertheless it's still quite hard at that high temperature, and therefore to test that reliably you need to have an indenter material which retains this high hardness, or at least that's beneficial. So if you have a small amount of tip wear at these very high temperatures on bulk materials, you can recorrect your data for that. So that's possible. And you can see in this work here that the effect of the irradiation is more noticeable at the higher temperatures. So if you want to understand that, again, it's important to test at high temperature. So we also need to consider the sample itself. So this is a somewhat wacky example. So this is a cemented carbide insert, as shown there on the right where it says before. So a typical cutting tool insert, so very similar to the one I showed you right at the beginning in the thermal image showing to 900 degrees. In this case, this one hasn't done any metal cutting. It's just been subjected to an oxidation test in air at 800 degrees, possibly in oxygen at 800 degrees. And what we can see there is that there's a dramatic swelling and really quite an unusual shape material at the end of it. And this is due to the formation of this brittle and porous tungsten trioxide. So this is obviously something that we want to avoid. So we can avoid this type of problem by indenting in an inert atmosphere. So an argon purge is sufficient to mitigate this problem in cemented carbide right up, in this case, to the example on the right up to the top temperature they looked at here, which is 725 degrees C. Because they were testing above 500 degrees, you can see that the group here has switched away from diamond towards a cubic boron nitride indenter, which, whilst it's not as hard as diamond, it's still pretty hard at high temperature, and it doesn't display the same oxidation problem that diamond does. So this is a popular choice, this combination of a cubic boron nitride indenter with argon, and this is our, by and large, this is our preferred temperature solution in the NanoTest Vantage system. So here we can see examples where we've used it on a tool steel, and also on a high strength alloy steel. And what we can see here essentially is that the softening temperatures are different. So if you compare sort of at 500 degrees, for example, you can see that the high strength alloy steel has dropped about 2/3 of its hardness, whereas the tool steel has only dropped sort of about 35% of its hardness. So this is, again, very useful sort of information. And this could all be done without the same indenter wear problem that you would have had if you did this with diamond. As I say, so this is a popular combination, this combination of using a cubic boron nitride indenter with argon purge. So you can just see on the left there, you can example of how we've got an environmental enclosure with the instrument in that. So so that's argon purged environment there. So this is a study from Virginia Tech, and here they were looking at the influence of temperature on silicon carbonitride thin PVD coatings around sort of 2 or 3 microns thick. And they're interested in this particularly because silicon carbide thin films have great potential for many applications, but they are intrinsically very brittle. And so therefore the guys there were interested in trying to understand whether they could produce coatings with enhanced nitrogen in there and mitigate the brittleness problem. And you can see here that actually they're quite successful in doing that. They could put too much nitrogen in there essentially, and when there's about 40 atomic % of nitrogen in there, which is the red that red curve there, you can see that the high temperature properties drop too much. But at these much smaller fractions, you can see really that the mechanical properties as a function of temperature are almost the same as the silicon carbide material. And the trend, the hardness versus temperature trend is a little bit unusual, and that's because there's a structural rearrangement that's happening at these high temperatures, right up to 650 degrees in this example. So another application area where it's been used is looking at thicker CVD coating. So this is some work by UC Berkeley. And here they were looking at 2 different alumina top layer compositions, so the alpha alumina and the kappa alumina. And what we can see here is that essentially there is a relatively complicated temperature drop in hardness, but nevertheless the kappa alumina remains softer throughout that temperature range. So I've talked so far about hardness. So obviously it's nano-indentation systems. If you have very accurate calibration and data analysis, then you can determine the elastic modulus as well. And this is particularly useful for tribology, because these two indices, the H/E, which is a measure of the elastic strain to break, and H³/E², which is a measure of the resistance to plastic deformation, are particularly useful indices in predicting the high temperature tribological performance. So this slide here, I don't propose to go into detail, just really to get across the idea that you can see essentially how this H/E index tends to decrease as a function of temperature, for, in this case, for a range of different tests with maximum temperatures up to 750 degrees with a CVN indenter in an argon gas environment. So when we look at H³/E², we see a similar behavior, but a much stronger decrease in mechanical properties on many of these systems. And what we can see is that many of the silicon containing coatings are performing much better. So this is something that's come out of this work quite clearly, that if we can incorporate silicon in our titanium aluminium nitride coatings, then we typically get better high temperature properties, which is consistent with its good behavior in cutting and forming applications. So one thing we do need to worry about, as I've said already, is whether the indenter material itself retains sufficient high temperature hardness. So this is some work from the literature gathered together by Wheeler and Mickler. So this is all non-depth sensing high load hardness testing that's generated this data. And what you can see essentially is that the hardness of all these different materials typically decreases as a function of temperature. So this is potentially an issue when testing coatings that retain high temperature hardness, particularly as coating designers get better and better performing coatings. So one of the things we're looking at is whether we can use diamond in conjunction with improved vacuum and fast heating and testing approaches, and we've been quite successful in that so far. As well as the hardness of indenter materials being temperature dependent, also their elastic properties and their Poisson's ratios are also temperature dependent, but these are much less temperature dependent. So, but it is useful in incorporating these temperature dependent properties in your analysis when converting from the measured reduced modulus into the sample Young's modulus at temperature. So this is as I showed you earlier, this is the NanoTest Vantage, or a NanoTest Vantage in a relatively typical gas purge chamber, and this is commonly used in conjunction with a CVN tip, typically if the test temperature is above about 450 to 500 degrees, and it provides reasonable mitigation of sample oxidation. And if you want to go higher, then we offer this NanoTest Extreme system, which allows us to do high vacuum testing. So it's got a very good vacuum level, and we've used this right up to, our customers have used this right up to 1,000 degrees, and this really negates any sample or indenter oxidation issues. So one of the applications where it's been used, I talked a little bit about it earlier, was on testing tungsten. So tungsten and its alloys, such as tungsten rhenium alloys, are really the prime candidate for the main plasma-facing material, protecting the structural components and the diverter and the like in a fusion reactor. So in these applications, these components are subjected to irradiated damage by alpha particles and fast neutrons at high temperatures. So typically, it's intended to study these things by surrogates involving ion beam irradiation. So this has the benefit of simulating the radiation damage, but not making the entire components radioactive. And the reason why is because the stopping distance of these ion beams is relatively small. So it's only the near surface region which is damaged. So when you need to, therefore, to understand the high temperature properties after irradiation, then you need to use a surface sensitive technique such as nanoindentation to do the testing. So the issue is, though, that if we were just to try and test a tungsten sample after irradiation, and we wanted to test it in argon at 750 degrees C, the answer would be no, it wouldn't be possible, because whilst at room temperature, the native oxide that exists on a metal such as tungsten is sufficiently small to be effectively negligible. Really, it grows quite rapidly at high temperature, and you get this sort of yellowy green, really quite horribly discolored and thick oxide layer buildup, and this makes it completely impossible to test on that surface and get any information at all about the underlying ion irradiation behavior. So the solution is to test in vacuum. And when you do that, so this is a sample surface just with a few indents in it, just to show that the at different temperatures, just to show that that microstructure in a tungsten alloy is completely retained after testing for large amounts of time. So at University of Oxford, for example, they've tested extensively right up, and they've held that vacuum for 28 days or 21 days maybe, without any problems at all, any evidence of surface oxidation. So it's a complete solution towards testing these oxidatively sensitive materials. So I mentioned earlier that time dependency was an important thing to consider in high temperature behavior experiments. So this is an interesting example on a polycrystalline tungsten sample where there's indentation curves at 750 to 950 degrees. And what's interesting is that over that particular temperature range, tungsten's loading curves are relatively constant. So it's almost athermal in terms of its behavior under loading. But nevertheless, the whole period of peak load, you can see there's increasingly more creep. And if we want to improve the accuracy of our elastic modulus measurements, we really need to come up with some strategies to mitigate this enhanced creep at high temperature. So that I've put some of them there. For example, we can increase the hold at peak load. We can combine this with a faster unload, and we can also combine it with a viscoelastic correction to the unloading data. So this is another example, in this case not from vacuum. This is a case on a back to a CVN indenter and an argon purge. So this is some work from I think Georgia Tech, and here they were looking at a solid oxide fuel cell glass ceramic seal material, which is particularly creep resistant at 25 degrees C, but under 550 degrees Celsius you can see the start of some sort of creep behavior in this 2-minute hold at peak load, but progressively at higher temperature you can see the transition to a dramatically increased creep. So you can see there that this high creep rate is continuing towards the end of the that holding period. So you can imagine as you start to unload that it's that rate is continuing to happen, and it's being superimposed on what's happening during that elastic unloading, and that's making it difficult to apply that elastic analysis to get the right reliable elastic modulus data. So at room temperature, this sort of behavior was thought about a long time ago by Feng and Ngan in Hong Kong, and they developed a viscoelastic correction to the contact compliance, which is, well, in terms of 1 over stiffness is a critical thing in the unloading analysis to determine hardness and stiffness. And they used the creep rate at the end of the hold period and the unloading rate, and they put that into that equation, and that allowed them to analytically allow for this continued inelastic deformation and improve this to get at the true contact compliance. And this was first done at high temperature by Sammy Tin and co-workers, and this is an example here on CMX4, which is a nickel-based superalloy, and you can see a couple of well, you can see actually 2 different indentation curves. So there's one at 30 degrees, which I guess was their room temperature, and one at 400 degrees. And it's not exactly said in this, but I think essentially as has been seen later, essentially over that temperature range, the hardness of this material doesn't vary too much. It's an unusual material in that sense. And what you can see is that in the unloading blue slope, the apparent modulus they've reported is 140 gigapascals, and the problem with that was that was too high compared to the literature value. And what they interpreted that was that there was continuing anelastic deformation, because they could see that transition to have that a large amount of ongoing creep happening. So what they've done there essentially then is they've applied a viscoelastic correction to that data, and then that's brought the elastic modulus right down to what they expected. So this methodology works quite nicely. We've probably done something rather similar with tests on tungsten and shown that that's very effective to get right up to 950 degrees. So another example now, similar sort of thing, in this case not on the superalloy but now on the bond coat, so that the bond coat mediates the stresses between the thermal barrier coat and the underlying nickel-based superalloy, and it can be quite thick, and it's shown here this M. Crowley bond coat, Amdrite 386, can be of the order of 100 microns thick. And again, it's a very, very creep resistant material. So at 500 degrees here, in this example here from our WTH Aachen in Germany, you can see actually that it's actually more creep resistant at 500 degrees than it is at room temperature. So it's very impressive. But as that temperature increases, you can see there's a transition towards creep-dominated deformation, and but 700 degrees essentially marks the operational limit of these materials. And although if you believe the analysis, you can apply, you can determine stress exponents from this data, and it notwithstanding whether you're really in secondary state creep or not, you can nevertheless determine stress exponents that are really quite close to other test techniques. So at high temperatures, as shown there by the stars on the right. So so these are the two materials we talked about earlier. So this is the bond coat we just talked about. This is work from Aachen, in this case on the same same nickel-based superalloy material as was studied in argon earlier, but in this case this is testing in high vacuum. I should have actually said that a sapphire indenter was used for these tests, and that's for reactivity reasons, because you don't want to be indenting nickel or nickel-based superalloys with a CBM, because you have at high temperature you have a strong reaction, and that will essentially blunt your tip. Just as an example that I showed earlier on steel and diamond, it's a similar sort of thing. So when testing nickel-based superalloys, then sapphire indenters are recommended. They're not as hard, but it doesn't matter so much because the test materials don't have the same high temperature hardness. So the requirement for high temperature hardness is different. So therefore chemical reactivity becomes the more dominant thing. So you can see in the graph on the right, you can see these things look very similar, but actually what is interesting is that the bond coat actually softens much more rapidly over 400 degrees than the superalloy, and that's potentially important in terms of understanding its and optimizing its behavior. So our future research directions really to understand that the critical issues in going to high temperatures are to some extent material dependent. So with hard coatings and materials such as the silicon carbide I talked about that retain high temperature hardness, indenter wear can become more important. When you're dealing with superalloys and other advanced metallic alloys, you need to consider the effects of oxidation of indenter inertness to avoid tip sample reactions, and also this greater sensibility to time sensitive deformation. So over the 20 years or so we've been doing this, we've built up a database of experience that allows us to have a good understanding of which indenter materials and which environments we need to use to test materials. And with that in mind, we've also been looking at, in conjunction with other people such as NPL, developing certified high temperature reference materials, either for testing in argon or testing in vacuum. And one thing I just touched on earlier, but it is very important, is to either check the tip shape at high temperature or immediately after cooling back down, because if your tip shape has changed, and particularly for testing bulk materials, it is possible to recalibrate for that and still get reliable data. But if you don't, your hardness and elastic modulus will be overestimated. So another research direction that's very interesting is, as I alluded to earlier, is this possibility to use a high temperature nanopositioning stage to target specific features in a complex microstructure or specifically design sample. So I'll go on to that in a moment. So as the technology's got more and more reliable over the years, the maximum temperatures have gone up. So this shows a range of different indenter materials, of which the NanoTest system is the pluses shown there. And it almost looks like a fairly linear increase, but if you study it in a little bit more detail, what you can see is essentially up until about 2010, that maximum temperature was really limited to about 500 degrees due to using diamond. In fact, the only result over 500 degrees actually was a micro-indentation result, where presumably they did get some tip wear. They ran in reducing gas, but presumably they weren't as worried because they were indenting so deep. But once CVN indenters were launched in conjunction with the argon purging, you can see then there's an abrupt change in around 2011 where it jumps up to about 750 degrees. Then it stays at that same level for a few years, and then around sort of 2015 is the first publications with the vacuum systems that we produced, and we launched the prototypes back a few years previously. So the last thing I'm going to talk about is this ability to precisely target individual features of interest, and we do that by having a hot stage in conjunction with a 3D SPM nanopositioning stage that we have on quite a lot of our NanoTest systems anyway. And this ability to nanoposition at temperature provides precise indent placement, and this can be done, for example, to look at individual phases. So in this case, this is a study from Francois De Luca and colleagues at NPL in the UK. And what they've done here is as a first stage, they've used the nanopositioner image. They've obtained that image of the cemented carbide material, cemented carbide cobalt material, essentially as an SPM image. So they're using the tip of the Berkovich under a very, very light loading to generate a map of the surface, and you can sort of see there you get exactly the same information as you do in an SEM image. And then they've used that image to precisely target where they want to put those indentations. And in conjunction with other analysis, they could determine which orientation the different grains of the cemented carbides were essentially. So you can see here, essentially the basal direction essentially is much higher hardness than the other directions. So the other thing maybe to show there is maybe just protect against any tip wear. They did the measurements at lower temperatures with diamond and then switched over to CVN, but that's certainly something you can do if you need to. A similar application in this case, the surface here, this is work from the University of Oxford, and what they've done here is they've focused iron being milled out micro-scale cantilevers in a material, and then they've used the SPM nanopositioning stage to get an image of that silicon micro. In this case, it's silicon, but they've done it in a range of different materials at high temperature. So you can see there a very nice image. It's not subject to any thermal influences, and you can use that image to precisely target where you want to put your deformation, so you can bend right at the edge of that cantilever if you wish. And they've done that, for example, to look at input changes in ductility as a function of temperature, changes in yield stress. So this is so these are results quite a long way above or below a brittle ductile transition in silicon. So on the left, you see typically a linear elastic loading until an abrupt fracture for the red curve. Excuse me. And at the higher load temperature, you're seeing a much more ductile loading where you get a lot of plasticity in there prior to fracture. And you can combine this, as you can see on the right, with some post-test SEMs and understand, look in detail, look at slip lines and things like that. Because the system is so thermally stable, it does give you options of different things you can try. So this is some more recent work by both Sharon Lee and Dave Armstrong at Oxford. And here Bo and Dave were interested in looking at the brittle ductile transition of micro-scale cantilevers of tungsten tantalum alloy. Essentially, so that they've done essentially load, partial unload, bend tests. And these tests across the temperature range really can pull out some very useful information which can go into fracture toughness calculations. And they were able to show, for example, as the temperature goes up, those lower load necessary for fracture and yield, and also greater ductility. I think it's also worth mentioning that these tests are quite long, so they have taken the advantage of the sterility. So they're loading and unloading and unloading in each segment at 10 micronewtons a second. So this is quite a slow rate. So you have to have a very, very thermally stable system. I suspect this would not have been easy to do at all on any other system, just due to this requirement in having this absolute thermal sterility. And they can do that, and as shown on the example on the right, or you go to the paper, you can see some quite nice brittle ductile transition data. So hopefully I've been able to show you how, this is my, well, very nearly my final slide, apart from the acknowledgements, how the high temperature nanomechanics really is now a fairly mature technology now, where it provides more relevant characterization than room temperature for materials that need to operate in these extreme high temperature environments. And the results from these type of tests really are helping our improvement of the understanding of the links between microstructure, mechanical properties and performance in these increasingly challenging environments. I've talked a little bit about how we can have various strategies to improve measurement accuracy by minimizing or ideally avoiding thermal drift, making sure that we have inert tip sample chemistry, eliminating sample and indenter oxidation, choosing the indenter material to avoid indenter blunting, and also to control both the loading history and also the analysis methodology to allow us to effectively cope with this greater time-dependent deformation. I talked a lot about hardness, but it's also not just hardness and modulus, and hopefully towards the end you can see some other useful information such as fracture toughness and yield stress that you can pull out of these things. So we are continuing to improve our technology, and we've done measurements at 1,000 degrees, so the stages themselves are not limited to that. We've run a lot higher than that. And as we go to higher temperatures, our challenges in working out what are the best indenter materials to use and for these different temperatures and these different samples. So there has to be a certain amount of flexibility. But we're quite confident that we'll be able to get up to 1200 degrees, hopefully fairly soon, but that's our project plan. To acknowledge lots of people on the left, so thankful for all the work I was able to show, but also providing figures on as well. Thank you very much to everybody there. And if you're for further reading as well, I recommend those 3 publications on the right. Okay, thank you very much. I think over to Sam, possibly, or Chris.
Yeah, sorry, just unmuting myself, pressing many buttons. And of course, I now have if the camera comes up. It doesn't matter if it doesn't. Okay, we'll leave it as it is. So thank you, Ben, for that talk. I don't see any questions that have come in. I'll just leave it open for another minute or so for questions to come in. In the meantime, I'll mention that if you do want further information, then you can see the webpage address there. But also do try the LinkedIn page, as I mentioned earlier, which also has links to papers and technical information on as well. Other than that, do look out for further announcements. We do a range of different seminars and over the course of the year. So we will, by going to LinkedIn, you'll be able to see and get, following the LinkedIn page, you'll be able to get acknowledgements, just to be able to get news of further seminars. Okay. On that score, as we have no questions come in,
we can email in questions. I would say that as well.
Oh yes, yes. So you can see if you might have a box on top of it, but if you remove the box off the top of the slide, you'll see Ben's email address there, which is Ben.
You're very welcome to email me if anything's unclear, or indeed I can also. I suspect you'll be getting from Service Ventures anyway, but I can also share this presentation if required.
Yes, we don't routinely share the slides through Service Ventures, but of course, Ben, you can share them directly with anyone who requests them from you. We do release the recording of this routinely to Service Ventures, so we will you'll get a link to the recording. But if you want the slides, then you should approach Ben directly. Right, so we do have a question here. Okay, from Yuwa. How significant is the elastic modulus decrease for both Indenter and sample at these high temperatures?
Well, okay. So there are equations, but they're not quite linear. So I prefer sort of, it's about diamond and CVN both decrease by about 4% between room temperature and 900, 950 degrees. So that then means that if you're testing a material that retains a certain amount of stiffness at high temperatures, such as we've tested, although I didn't talk about it, we've used diamond up to 900 degrees in vacuum. And in that case, the coating that we were testing was something like 400 or something GPa modulus at 900 degrees, and it was about a 2% difference in that number by using the right elastic modulus to, in the calculation from reduced modulus to sample Young's modulus. The Poisson's ratio is essentially doesn't really come into it. Sometimes the work from James Gibson and Sandra Cortical they do correct for Poisson's ratio, but I don't think it's absolutely essential. Just in practice, it's good practice maybe to do so, but it's such a small percent difference that you're not going to easily see any effect of it.
Thank you for that question. There's no more that have come in. So on that, as we have hit the top of the hour exactly, which is when we're due to finish, I'll bring the meeting to a close. Thank everyone for attending. Thank you, Ben, for speaking and preparing the talk. As you see, there are various ways to contact us, and we're always here to answer questions about high temperature or indeed any other form of nanomechanical measurement. So on that, I'll say thank you very much, and I'll close the meeting.
Yeah, thanks so much, everybody. Thanks for your time. Okay, bye-bye.